Good morning, everyone. Welcome to another episode of Xa Talk Show. Today is September 10th, 3 o'clock p.m. San Francisco time, Tuesday. Okay, so now I'm alive. This is my second try and it's success. So, good morning, Zitron. Good morning, Bartholomew. Good morning, Justin. And what will today's topics be? So, guys, type a topic. And meanwhile, let me close my door. Okay, type a topic and we can do technical, which is programming, JavaScript, Emacs, Emacs Lisp, or Golang, or we can do non-technical. But I'm thinking not non-technical because we did a rant about open source and stuff yesterday, and I think the day before. So what topics? Number six. Let's see, number six. Now this is like an JavaScript, TypeScript, SVG, write a function plotter. Okay, let's do that. Let me close my door. Okay, so I'm alive. Check. And live, 6 people watching. Great, fantastic. So Bartholomew says topic number six, which is JavaScript, TypeScript, SVG, DOM, on writing a function plotter. Okay, so let's get the window here so you can see. So okay, so over here and this window over here, that should do. And on the left window you can see all my Emacs commands, such as moving cursor and so on. And okay, topic number six. JavaScript, TypeScript, and JavaScript, TypeScript. Okay, so writing a function plotter. So okay, so let's go to this is today's talk show page, and let's go to Xadro. Okay, go to here, this directory, and go to test 2018 index. Okay, and copy the URL, open the buffer, show it. Okay, so I'm thinking what to do, like what how shall we do this. So I've been trying to work on this project for a long time this on and off for a year now. So this is written in 2008. It already does that, but it has problems. So for example, you can see, so here is the code. There are two plots. Those are, you just call the function parametric plot. And parametric plot, which element to attach to, and here's a function. So x and the function is sine x squared. Yeah, so and from 0 to 7. That is the first plot. And the second plot is sine times sine x times pi. Good morning, Dion. Great to see you, Dion. Great to see you on Twitter, and I get to see your face. Greetings, greetings. So what's the difference between parametric plot and normal plot? This if you have not done calculus, you may not know, but it's so simple. Normally when you plot x, Okay, let me explain this. Like normally, you plot something like sine x, right? Basically, y equals to sine x. So parametric plot is, instead of that, um, you have this. So x equals to a function, t, okay, and y equals to a function. So as t goes t goes from 0 to 10, for example, so you plot, you evaluate functions f and g, and t from 0, you get a pair of numbers, you plot it x, y. When t is 0.1, you get pair of numbers, and that's x, y, then you plot it. And you can see, and the normal plot with respect to parametric plot would be like this. Let me show you. Okay, so the normal plot, x equals, normal plot in terms of parametric plot, it's just like this. X equals to x. So x doesn't change. X is just, 0, 1, 2, 3, 4, just going a linear, a line, basically. Yeah, x equals to x. Yes, yeah. Wait, let me change the parameter. So this is a normal plot. So parametric plot is just more general, and so you can use it to plot, normal curves. Okay, so I did this project, and you can plot this, but there are many things to fix. Okay, but I'm thinking, what are we going to do today? Are we going to? Okay, so hold on a second. Let me go back. So go back to the. So this is a file, right? This is the file that does the two plots, and so this is the code, but you need the library. So library is this one. Go to the bottom. It's 500 lines, and there are a lot of problems I need to fix. There are quite a few problems, because when you start to learn SVG, plot JavaScript and all that, the thing with the details. It's the difficulty are always with the details, because theoretically you understand how to do it, how to draw a circle and line and so on, but the details, there's a lot of details, and I have a lot of things to fix on these. For example, the font size, the plotting the axis with labels, that's one of the most difficult part actually. Plotting the labels and axis, that's one of the difficult part. So Dion says, can't say how long tonight, but I have a question. You have info on writing parsers in Emac Lisp. Will you do a show sometime about it if you know about it? Actually, I don't have info about writing a parser in Emac Lisp. Yeah. Right now, my understanding of parser is very limited. So I have not actually written a parser. It's one of my project to do. It's so many things to do, like in learning Julia. Okay, so but writing a parser is one of the thing I want to do. After you are able to write a parser, okay. Let me show you that. Compiler tutorial. Okay, so here's a basic tutorial about writing how compiler works. It's not actually about how to write a compiler, but how the outline of compiler. So basically, you have the parsing steps, then you have generating code step. So parser is very interesting, and I haven't got, I do not have full understanding on how to do it exactly, how to write it. I mean, the point is you have to be able to write a parser for a programming language. It's a bit involved. Okay, so because normally, like parser, when a programmer says parser, there are so many different meanings. For example, if you write a regular expression to extract emails in a HTML file, you can call it parsing. Normally you just say, oh, I'm gonna parse this HTML to get all the email addresses. That's parsing. But or you read a Unix config file. Unix config file is usually like x equals to 3, window size equals to 699. That's kind of like Unix config file. You want to get the value and set it to variable. That's also parsing. But these are all parsing, but that's not what parsing means with respect to compiler, with respect to programming language parser. Okay, so in programming language, parsing means it means your program needs to read a grammar file, formal grammar, basically backwards no form. So you might read this page. You have to so you have to you have to learn the formal grammar. Then your program is going to read the formal grammar, and then be able to parse any text, any sequence of a text, and turn that into a tree, a syntax tree structure. Then that's parsing. Okay. Once you after that, then you do the semantic code generation, like compiling. That's a compiling part. I mean that's the code generation. You spit out C code, you spit out assembly code or whatever, or that's two parts to compiler, parsing and code generation. So parsing is very interesting, and it's quite detailed study. You might study at least half a year to a year to begin to write the parser. And there is tremendous theoretical aspect to it, like theoretical computer science, because parsing in a sense is actually the formal language. You're dealing with formal language, so that's when you're dealing with lambda calculus and all that. So parser. So actually, I don't really know about parsers that much, and I have not written a tutorial about it. So so I do not know, and obviously I do not have a Emac list tutorial about parsing. Yeah, so yeah, I will not be able to do a parsing, for tutorial video. But what I can do is like I grope, like I do it live, and I kind of like learning with it with you guys together. That's actually I don't know enough about parsing to actually do that. Julia, yes, party. So okay, so let's go back to JavaScript. And okay, so I need to figure out what is the plan to write a write a tutorial about plotting curves. Um, I think the best thing for you for the audience is actually to start from the beginning. I mean, the alternative is just to follow. The alternative is just to okay, you guys make a choice. The first choice is I'm going to start from scratch. I'm going to start from scratch and write this. So this way you will learn from scratch how to create this from scratch. It will be 1 hour. Okay. That's one way. That's choice one. The second choice is I'm going to explain my library. So these 500 lines of library. I mean, I'm going to use my library to, basically I'm going to, let's see, I'm going to explain this code. You see, I'm calling my library is so simple, just one line. And then you can plot it. And I'm going to explain that. I'm going to explain the library code, how it works. So this is choice two. So number one or number two, guys, type it. So Dion says, fair enough. Thanks for the link all the same. It's something I definitely want to get into. Yeah. So yeah, great to see you on Twitter today. Uh, Adios, bot. Remember to save. So what's going on, bot? Remember to save some chicks for the rest of us. Oh, you gotta go. Okay. Uh, okay. Ztron, guys, Ztron crazy and bot. So which option? Plot a curve from scratch or explain the library. My library about plotting curves. Yeah. So type the answer. Let's see. Type the answer. Like, let me know what you guys prefer. Explain library. Okay. So okay, let's do that then. Uh, so I got Lisp. I got this log function. All these are in SVG and logistic map. I haven't done that yet. Geometric inversion. That's not done yet. Okay. So explain the library. So okay. So you see, this is all SVG. It's not bitmap, meaning so because you can see, you can actually select, uh, you know, select text in it, and because it's SVG, so it's like scalable. It's smooth all the way. One thing interesting about plotting is that you see all these dots. Each time this red dot happens, that means there's a point. Then you just connect point to point to create lines. Now you see, when when the curve turns very sharp, there are a lot of points. This is called adaptive sampling. This is what you need to do, because otherwise, when you plot a curve, you will see, you'll see kinks. So the technique is that you measure, you plot a bunch of points of the function. You plot lots of points on the function. Then you measure the angle. So there's one point here. Let me show you. So there's one point here, one point here, and another point here. So you have like that, right? A curve. So suppose there are 3 points. Then you want to measure the angle, between two lines. If the angle is like flat, then that's good. If the angle is greater, than some degrees, not very flat, then you want to add another point, in between. That's how you get it to be smooth. You see, even for this one, this is not so smooth. You see here, you see this point, there's kind of a kink you can see. So if you remove the points, if you remove all the red dots, here, people will see kind of a kink. That's not what you want. And there are quite a lot other issues. For example, there are some monster curves that just goes infinitely infinitely non-smooth. Like, there are some examples. Maybe I should not show it because we need to focus on the JavaScript. But anyway, so there are some called badly pathological curves. Mathematician created, because they need to study. When you study calculus, you need to study smoothness of the curve, differentiability, and so on. So there are some monster curves, so-called monster curves, that when it gets near zero, it just go up and down. The more closer to zero, it goes more wild, up down. So it becomes infinitely, as it approaches zero, it becomes infinitely dense. Actually, that's interesting. Monster curve. So I'm just let me just talk randomly, then explain the library a little bit. Curve monsters, monster curves. Wikipedia. Space filling curves. Okay, space filling curves is one of the example of pathological curves. Um, Well, let's not get into that. Okay, so let's um, explain library. Okay, let's do it. Thank you for the reminder. Okay, the library. Okay, so the library is, it's only 500 lines, but there are a lot of functions, and um, it, we cannot explain them all. We have to kind of explain. Actually, I think it's actually better if we just start from scratch, because if we start from scratch, basically that's what this library do. You see all the basic fundamentals of what this library is. Because if I just jump to the library, it's a lot of rather boring technical details. Like for example, let's begin. Okay, let's give some flavor, then maybe we can switch if you see it. That's better. So for example, first of all, you have a bunch of functions. First of all, okay, define constants. Okay, I'm defining some constants, so I can just write cosine instead of sine dot cos. Okay, so those are constants. Now f range is a function that just generates a array, like from 1 to 10 or 1 to 100 with increment of 0.1. So you need this frequency, because when you want to do a plot, you want to say x from 0 to 1 or 0 to 10. You want to have an array. So f range, that's the range function, like the range in Python. Okay, and then you have split array. Split array is like so you have one array, but you want it to become nested subarrays. In other words, you say partition. Mathematicians call it partition. So one array, you want it to become several nested arrays. Like there are certain points you want to cut off. Why do you want to? Why do I need this function? Because when you plot a curve, let's say from x to 10. Now, for some functions, some value x will become infinity. That happens. For example, if you say so many functions, that happens, x becomes infinity, or you have divided by 0. So those are bad points you don't want. Actually, so these are technical details about plotting curve. When you start to write this, and when you plot, for these textbook examples, they are so nice. They are so just nice. 0 to 1, 0 to 10, everything is nice. But in real life, given a function, it's likely you'll just go to infinity. Anywhere go to infinity, or you have divide by 0. So you need to handle that, because otherwise, the JavaScript, they becomes a none. You got a number NaN, not a number, because either you are dividing by 0 or it went to infinity. You got infinity, and you cannot plot infinity. For example, y becomes infinity. You cannot plot it. So you have to. So when that happens, you have to actually, you have to know which point that happens. You cannot always know which point that happens unless you do symbolic mathematics. So there's a lot of issues. So you don't know which point that happens. But however, because you are computing the function at many values, you kind of know which value becomes very large. Like it becomes 1 followed by the maximum number representable by JavaScript. The 16 bits or 32 bits float. So you want to find those numbers. Then for example, when y goes to infinity at x equals to 0, for example, you want to find that pair of points, and you want to, there are a lot. The question is open. There are a lot of ways to handle it. You could replace it just by, just leave it be. As long as it's not infinity, just leave that value be. So you are going to have a line that shoot up, or in the case of parametric plot, the line can shoot into any direction. Like, because you have a huge value of x, y, so the lines goes, any direction. Then so actually you have lots of problems. But anyway, let's go back to the library. So f range is a range function like Python range. So this function split array, it I use this function to, whenever there's a value of infinity, you remove that point and split it into two arrays. This is called partition in math. Okay, so split array function. So far, it's very simple to understand. So all these functions are very simple to understand. This dot product of two vectors. That's all these functions are math. All these functions are math functions. That for example, vector dot product. It takes two vectors, one vector, then the second vector, then you return this value, which is the dot product. Now this is useful to find out when you want to find out the angle between two lines, two vectors. So all these are math. So this is a vector length. This is a unit vector. Unit vector is like, so if you have a vector, a vector is just a pair of number like x, y. Let's say x is 3, y is 4. So the pair of number 3, 4 is a vector. So what does that mean? It just means, it just means 3, 4, it's a point. So a vector, you think of it as a arrow from 0 to that point. So that's a vector. Basically, a line segment, or a directed line segment. So that's a vector. So what's a unit vector? Unit vector is a vector in the same direction, but you want the length of the vector to be 1. So that's unit vector. Usually in math you call this normalization. Why do you want the vector to be length of 1? Because in many ways that makes a lot of problems simpler. So when you have a vector, you often want to shorten the length, so the length is 1. So this is how you do it. So this function, it takes a vector, which is an array of two numbers, then it returns here is functional notation. Here is functional programming. Let me show you. Okay, make a backup. Let me show you what this is doing. Okay, so this function takes a argument. This argument is a pair of numbers. Okay, now the body of the function is this one, two parts. So it's made up of one function evaluated at this value. So Bartholomew, yesterday we were talking about function return a function. So here is actually an example. We found it. So the way I define this function is that first of all you create this function, then you evaluate it right away by giving it that argument. So let me show you another way to write this. Am I doing good? Like right now we are not explaining anything about plotting at all. So if you like to skip this, we can. Like just type. Okay, type. Tell me what whether I'm doing good or bad, or what else you wanna know. So right now I'm going to rewrite this function in a more normal way. So a normal way to write this is like this, okay? Okay, so that's that tt equals to that, and um, tt. Okay, here is alternative way to write this function. So you first of all assign this can be constant actually. So you assign a value of this expression, then you map the vector. You apply map to the vector. Remember, the vector is the input of two array of two numbers. You map each element by x divided by tt. So this is actually very simple, and actually we can write it this way. We don't even need that. So this is how you do it. So okay, so actually we don't need even return either. So we can do it this way. So there. Here is another way to write it. Now you might think, okay, so why do you write this so complicated way? Why don't you just write it this way? Because because for efficiency reasons, okay. Anyway, let's not get into that. For efficiency reasons, keep explaining. Okay, so wait. Okay, so let's do it. Because this is actually difficult to understand. Unit vector. Let me just explain what it is. It's simpler if I just type in. For example, a vector. You have x, y. That okay. Let's say a, b. Okay, that's a vector. So what is a unit vector? A unit vector is this value. Okay, this value a. Um, Square root a squared plus b squared. Okay, a divided by square root a squared plus b squared, and the second argument, the second component is b divided by square root a squared and b squared. You see, so this square root a power a squared plus 2 squared happens twice. So this is the math definition, okay? But when you want to code, you don't want this square root appearing twice, because depending on the language, the compiler is not smart enough. You will actually compute this twice, so you don't want it. So the best thing to do is to compute a square root, assign it to a value, then you put a value here and here. That's a thing with translating math formula to programming language. There are all these efficiency issues. Now some compilers, today some compilers are smart enough that when it sees a expression repeated, it'll just compute it once. But you cannot rely on that. That does not always happen. So that is why you wanna do this. What I'm doing. So actually, yeah. So Chokov. Hi, Chokov. Okay. So anyway, that's a function about normal vectors. You can all this math concept. You can look up Wikipedia. You can look up unit vector. You'll see it. Vector length dot product. This is dot product. You'll find it on Wikipedia. So this one computes vector angle. Let's not get into it. So this is vector addition. All these are simple. Okay. Then vector subtraction. scalar multiplication with a vector, then here's a matrix multiplication with a vector. Okay, now this is a rotation matrix. Why do you need this? Because you want a point and you want to rotate it around the origin by alpha, by angle alpha. So you want to rotate it, then you need use rotation matrix. That's how you do it. So all these are linear algebra. Then you want to rotate a point. Okay, so then you have radian to degree, degree to radian, and this one. Okay, this is another technical detail. This is get curve minimum and maximum. So basically, this is you have a bunch of points, lots of pair of points. You want to find you want to find the boundary. So why is this useful? So you can find out what range to plot. Like from 0 to 10 or 0 to 1,000, and y is maybe from -10 billion to -10. You need to find out the plot range. Basically, you need another interesting thing is that why do you need to do this? Because, for example, in this textbook, school textbook examples, they are all nice. You just plot from 0 to 10, whatever. But in real life, a function, they can go from -1 billion to to whatever, and same thing with y. So it's unpredictable. So you can so you plot a lots of points. You need to, and you want it to be automatic. You see, this is a critical feature, very useful. This is a difference between good software and bad software. You want this feature to be automatic. In fact, to write a curve plotting involves somewhat AI, artificial intelligence. And this is a good example. Like what range to plot, because in real life the points can be anywhere. Okay, so why do you want it to be automatic? Because if it's not automatic, it is almost impossible for a user to find out where is the actual curve. Because for sine and cosine, we know those are pretty examples. They're so simple. It's just centered on our origin. But in real life, it could be anywhere, and it is actually impossible unless you already know. You have symbolic analysis of the function. Like textbook functions, sine, cosine, log. Those or polynomial. How they behave. But in real life, if you are a scientist, working for NASA, you have complicated function. You don't know where it goes. So so if you don't know, it's impossible to go by trial and error. Because if your range, let's say if you try x equals to -1,000 to 1,000, it may show no point because it may not be there. But even if it shows some points, all the points is like little. You have to spend like hours to find out where the point actually are. So you want a feature that automatically in some smart way to find out where is the interesting part of the plot. And this is not trivial. Okay, because the way I do it here, you see, this is a dumb guy's way to do it. The simple way. The simplest way is simply to find the minimal x, the maximum x, the minimal y, the maximum y, and that is your border. Okay, but that's no good, because for some curves, they all the interesting parts are concentrated in an area. But far away, you might have one point here or there. So that happens. So then this is no good. So you see what I mean? So this is a problem. So this is my solution, my simple solution. My beginners first try. Just find the maximum and minimum. But that's not good. But if you really want to do this, you need to have basically you need to do some statistics. So basically, you have a bunch of points. You want to find out the distribution, some kind of statistical distribution. Then you find out, then maybe, all the points actually are concentrated over here. Or if they are kind of equally distributed, then this minimum maximum works. So for example, this is rather equally distributed, all over the place. So that's interesting aspect. So this is the get curve minimum maximum. That's okay. And this is the most actually difficult. This function is most involved. Add points. So it takes 1, 2, 3, 4, 5 parameters. 1, 2, 3, 4, 4 parameters. Then the function is like that. So what does it do? So like we explained before, you have adaptive sampling. You see, basically, when the curve bends, you want more points over there, so it's smooth. I wonder if I should show example to actually try to remove the dots so you can see the difference. So you see, why am I plotting the red dots? This is actually a debugging plot. So I can actually see, where are my points, my dots, because otherwise you don't see them. You just see a curve. You don't know where the dots. So this is kind of a debugging plot. And similarly, you want to try a different curve. So for this curve, this is an equal angular spiral. This curve has a property that all the angles, doesn't matter which point on the curve, you can pick any point on the curve, it has the same angle. Okay, so that's a special property of this curve. So when you want to test your adaptive sampling algorithm on curve, you can try it on this. So on this one, you can see it works. So it's working well. And of course, you also want to try this on this curve. So why do I plot these two? Because this one you got more sharp turn, very sharp turn. That's why I use this curve. And this one is typical sine. You have very smooth turn. So anyway, so this is about adaptive sampling. When the curve turns more, you want more points there. And the heart of that algorithm is this one, add point. So what that do is that, okay, you have sequence of points. Each point is a pair of numbers. You have a sequence of them, like a list or array of them. So you want to measure the angle between points. Like every 2 points forms a line. So at each point you actually have an angle. You want to measure that angle. If that angle is not flat, is not like 180 degrees, then you want to add another point in between, like on the left or on the right. You want to add another point, from the function. So that is what this function do. Given an array and given the maximum angle you want, this okay, the first argument is points. It's an array of points. The second argument is a function. It is a function, that the parametric function that plots the curve. Okay, because you need a function, because you need to call the function when you want a new point. So the third argument is the max angle. It's like an option you can specify. Then the fourth argument is recurse level. That is how many times you want to do this, so this is getting technical detail. Because why recursive level? Because there are many approaches to how you generate new points. So the way my approach is using recursion. That is, given a bunch of points, I do it one shot. Then I got, then I got more points. Then I can do, recurse, do it one more time. So how many times I want to recurse, so the more recursion, the more smooth my curve will be. But you don't want to, you don't want too much, because you don't want a million points, because that's gonna crash the browser or slow down your program. You want just the right number, so that it doesn't, kinks like this doesn't happen. You don't see sharp bends. That doesn't happen. So that is what this function is about. So far so good, Bartholomew, and all you guys, Zitron, Crazy, and how many people are watching? 7. Okay, so say something, guys. Let me know how am I doing. So that's what this function about. Add points. So let's jump to the next. So far so good. Okay, great. So next function, we have this translate string and scale string. Okay, what those are, when you do this kind of thing, oftentimes you want to scale the whole thing, magnify or shrink it, or you want to rotate the whole thing, or you want to translate. In math, you call translate, which means move the whole thing, up or down, or to somewhere. That's mathematical operation. That's part of group theory. All these are called isometry. That's some tech jargon. So okay, look up isometry. Look up anyway. So you want to do that. Now SVG has a way to do that. Okay, now so we starting to get into SVG. So let's go to SVG. Okay. Now remember, to do this, you need to know JavaScript. You need to know DOM, because DOM ties everything together. DOM is basically the browser, controlling how you generate these things. Then you need to know SVG. SVG is the actual okay. Here's my you see. Here's my another JavaScript app to generate a arc. Very difficult in SVG. Anyway, so this is my SVG tutorial. So SVG, when you do SVG, first of all, let me show you a little bit what SVG looks like, because all these all these plot you are seeing SVG. Let me show you. Okay, yeah. So let me show you part of the explanation. So let's show the source code. Open that. So let's magnify. So you see all these. You see all that. Let me. Okay, you see this path element. You see this G is for grouping. So first of all, in my source code, I have a div ID equals to SVG plot 1. Okay, then everything below it, everything inside it is generated by JavaScript. So this is the actual output of the JavaScript. So you see, so you got a group, then you got a group, then you got path. So this path, this one is actually some points there, some segment. So this is another segment. So let's go down. You see, so you got lots of actually it shows there. You see, those are the vertical lines. Those are the background vertical grid. You see, so the browser actually shows it. You see, so those are the vertical grid. Then you have let's see. Okay, then you have these are the path. This is the blue lines, the actual curve. So you got thousands of points, probably 1,000 or two. Then you have these are text. Okay, so these are the labels. So what you see there is the SVG. SVG is XML. Okay, it's just like HTML. So your job when you write this plotting software, your job is simply to generate those elements. You know, it sounds simple. Actually, so you can actually use Python or whatever other language to create this and show and just show in browser it'll work. So your goal is actually just to generate these elements, these SVG elements. So let's see. So these are text. These are the vertical, the y-axis labels. Then what are these? These are the dots. Okay, let's show. Okay, so you can see dots are circles. Oops. For some, okay, now it shows. Okay, so you see, you can see in the browser over here, it shows the circle label. I mean, those are just the dots, lots of dots. Okay, so that's the SVG. That's what all these code are doing. So back to this function. So SVG. So back to SVG. So you see what SVG is like. And SVG has a feature that is. Let's go to SVG. SVG has a feature that allows you to do transformations, coordinate transformation. Let's see. Yeah, so you see this translate, scale, reflect, rotate. The way you use it is like this. For example, here is SVG. We say SVG tag width and height. Then you create a rectangle. The x equals to 0, y equals to 0. That's a coordinate rectangle. And color gray. Okay, that's the first rectangle there. And this is another rectangle with the same coordinate. You see x0, y0. But however, you have this string, this attribute. It says transform equals to a string. The string says translate 2040. So this is how you use how the SVG translate works. So you have this bunch of functions: translate, scale, reflect, rotate, but they needs to be a string. You see, because this is not a programming language exactly. So these functions are actually inside a string. Then you say transform equals to that string. This is one of the very annoying thing about CSS and SVG and XML. Because when you do things inside a string, that's extreme pain in the ass. So anyway, but that's how SVG is. Yeah. So here is the line. That's what you have to say. Same thing for when you want to scale something. So if you want to use this in your JavaScript, again, there are many ways to do it. Like if you want to move a graph, there are many ways. You can directly use JavaScript to translate the points directly, or you can add to your SVG this attribute, transform equals to something. And it seems that using this way, using SVG is actually faster. because SVG, SVG is so-called declarative, declarative language. Okay, so and because it's implemented in browser has optimization to death. So when you do this, when you specify SVG, transform something, it's faster than when you actually do computation on thousands of points in JavaScript. So that's why I have these two functions. Because generating a string is a pain, so I have a function that generates a string, the translate string for you. You see, this is a string, translate. Okay, so okay, bye Zitron. Good night. So okay, so I think this is kind of boring. Am I right? Zitron crazy or any other guys watching? Uh, 6 people watching. Okay, so the next function is creating a SVG element. So we are actually starting to get into SVG. So what this function do? This function actually just create this element, like like this SVG width height view box XY, things like that. And basically you use this built-in function to create a SVG element. So you say document.create element ns, and a bunch of things. That's how you create a SVG element. So this function just create a SVG element with with attribute like width and height, like that. Okay, so I'm not sure this is going well. So Bartholomew, what do you say? Uh, so we have creating SVG element. Yeah, because this code is real life code, and real life code you have a huge amount of things you are not interested, as for beginners. And also this is written in TypeScript, so you got all these incomprehensible kind of crap. So I think actually to learn. So Bartholomew says it's interesting to see. Yeah, okay, so yeah, so I guess it's interesting to see real life code once in a while, um, because I mean, like I'm thinking like right now, after this, you wouldn't be, you wouldn't be able to start to write one, write a SVG. But however, if we start the beginning, you would know after 1 hour, you would know you can start to write from scratch. You can start to do it, but not from explaining this code, because when I explain these things, I'm explaining their concept, what they do, but but I don't explain the code. Like you don't see the code, what because it's fairly complicated. Because it's real life stuff. It got lots of error checking and lots of other type things. But if we start from scratch, it will be very simple. You see what the whole thing. I mean, you see kind of the whole kind of architecture. Actually, I have an example here. So if you want to learn SVG, the basic, just like if you want to begin to write this SVG clock, you can by reading just one page, by reading this page, scripting SVG. So here we have a SVG of a red circle, and the entire code is just this, 10 lines also, 15 lines. And this entire code kind of kind of represent the whole, all this complexity, kind of. That's the bottom line. So that's, this is the foundation. To draw a circle, you can see how to use JavaScript DOM to create SVG images, and this is the fundamental. So this you learn first of all, you need to create a HTML element. That's so you can tell JavaScript where to insert the SVG. Then in your code, you generate a SVG element. Then you generate, you add width and height attribute. Then these 5 lines is how you generate a circle, SVG element. And in fact, every other SVG element is the same. They are just different. Like you have rectangle, you have path, you have other things. But basically, the code is the same. That how you generate a SVG element. Then you set the attribute, like the center of the circle, the radius. For rectangle, it basically is the corner of the rectangle, and width and height, things like that. You create a SVG element, then you set the attribute. That's how you do it. Then you attach the SVG element you just created into the SVG tag. Then you attach that to the ID, to the HTML place. So meaning that you insert it. So that's how you get this image. So it's this is the outline. And all these code are doing that. All this code basically, for example, let's see, we explained one of the code, this code create SVG. This code is basically this single line. It just create a SVG tag. But why do I have so much code here? Because this is a library, so it's for convenience. The SVG tag, you have the attribute width, height. You also have optional attribute called viewbox. That's how you specify user coordinates. Okay. So if you do it raw, then you're gonna write it like this. First of all, first you create a SVG element, then you set attribute width, set attribute height, set attribute viewbox, then 4 values string, things like that. But this is inconvenient. This is tedious. So you have this one single function with so the way you use it, for example, let me show you where I use it. So search for this, go down, there it is. So you look at this line, this is how I create a SVG. So you just call create SVG, new means the first argument is the parent, meaning where do you want to attach this SVG element to. For example, in this page, we need to attach it to the div. Like where do you want to insert it into the HTML. So the first argument is the parent. Because here I don't want to attach anywhere, so I say no. And the third argument is the width and height. I don't want any, so I say no. Now remember, no is different from width equals to 0 or something, because when you say no, you do not even have the width or height attribute at all. Those are different. So anyway, so I say no, then I give an array of 4 elements here. You have x min, y min, x width, y width. that's the view box attribute that specify the user coordinate. Because if you do not specify user coordinate, then it's just the pixels. For example, in this plot, from the left border to the right border, there are maybe 800 pixels. So if you do not specify user coordinate, then your coordinate is going to be, you're gonna work with from 0 to 800. And when you plot a sign, you have to translate your coordinate into the pixel coordinate. So that's a pain. So you can SVG, you can specify a user coordinate by what's called a view box. I have tutorial here. You can read the view box unit user coordinate. So anyway, so you see, so I call this function is kind of nice. Everything there, just one line instead of otherwise. Otherwise, I would have to say. Otherwise, it's going to be like 10 lines. Otherwise, it's going to be like this: create SVG element, then set attribute, set attribute, set attribute, then append child. It's kind of like that. So that is why. So you see, now you see this function. So let's go back to the definition. So that's the function. Okay, that's function. So then here we have another function. So hold on a second. Let's take a break. Let's take a break and see where are we going. So Bartholomew says maybe you can focus on like 20 complicated lines and explain them in far more detail. Okay, then yeah, maybe let's do that. Forbidden says it's like low level GUI code describing elements. Yes. Okay, so great. Thank you guys for the comments. So okay, Bartholomew says maybe focus on something and go in depth. Okay, so okay, so let me think what I want to do. Okay. So anyway, so far so good. So actually, the rest is not much. Almost all the rest of them is about generating SVG elements. Let me show you. Okay. Yeah, we go through this. So you see, so we have a function that generates. As you've seen, we have this function create SVG element. That's the first one. That creates a SVG tag. Then you have this function. This function generates a okay. So this function generates a elliptical curve, which I kind of showed a little bit there. Why? Because let me show you. Now SVG is kind of, it's not, all these standards DOM, it's very, they got lots of problems, lots of extremely weird. It just sucks. Like if you know math or if you know programming, I mean either camp. If you know math, you know how to specify a Lisp, their parameters and so on. If you know programming, you know how to write a function and so on. But when it comes to DOM and SVG, doesn't matter which group you are, you find lots of incredibly you find like, why would somebody, like, what the fuck, why would somebody create something like this, because every time you want to use it, it's very tedious, not just tedious, but it's like it's very badly designed. You'll find that a lot in DOM and SVG, just like Unix. Okay, just like the Unix shell and and many programming languages. As a programmer, you swear all day. Like what are they thinking? Why is it this way? There are a lot of reasons. So basically, mostly because social reasons. It happened that way. And more specifically, SVG, it turns out I looked into, I studied the detail. I tried to trace why is it this way. Like who designed it? I mean, is it we tend to think, okay, someone who is a great coder who designed it, something like that, then it becomes standard. No, typically that's not the case. Typically, it's either committee or nobody cares. Okay, like SVG is like that. It's like nobody really cares, but it so happens you have this standard, and seems like people say, oh, this is the standard we need, but nobody care about it. Commercial organizations like Apple and Flash, in particular Flash, they do their thing. They don't give a fuck about SVG. They care about their design. Apple has, Apple invented Canvas. Okay, Apple has, anyway, Canvas, that's Apple's invention. Then the Flash, the Macromedia back then, Adobe Flash, they care. They have action script. Basically, is like action script is basically like JavaScript, but for their stuff, Flash to code Flash. So for like 10 years, Flash is everywhere, and it's fantastic. You can create clocks. All the clocks are written in Flash. Puzzles, games, 2D games everywhere. But SVG is like, SVG is actually very old, beginning around year 2000, 1999, something like that. But SVG is like someone, like every programmer says, oh yeah, we need this, but actually nobody cares. They just, like most programmers, they, yeah, open source and all that. They don't actually have, like if something went bad, it doesn't matter anything to you. Nothing happens to you. That is when all the bad things happen. Like when you buy something, you have to pay, right? Then you carefully choose, oh, which computer should I buy? What memory? You spend the time to research. But if you are a professor, you are telling students to buy textbooks. You don't care. You just care what book is good for you. You don't care how much it is. That is why the textbooks becomes $300 today. Anyway, so SVG is like that. SVG, every programmers and the big companies, say, oh yeah, we need this, but nobody gives a fuck. So it turns out people just like people who don't really know things, they just create it from scratch. Lots of bad designs, and in particular, you should go read. There is a woman who participated without pay. Okay, this happens a lot in programming in lots of these standards. So she is not expert, but she became an expert. Because she started to study SVG. So she became an expert, and she participated in the standard process, and she also wrote SVG books on SVG2. Okay, it's a fantastic blog. You should go read it. Okay, so there's this girl. I forgot the name. I can look for it, but I forgot at the moment. Anyway, it's a woman who has written at least two SVG books published in the past 3 years. Okay, go to Amazon, you'll find it. SVG books published in the past 3 years. She has written at least two of them as co-author, at least. She is also participated in the SVG2 standard, which I think came out within the past 3 years. Okay, find her name. Then find her blog. She has written a blog about SVG2 standard. Like she tells you the experience, how it all happened. You read it, then you realize it's like it's like very bad. Okay, it's like very extremely bad. So anyway, back to the topic. So my point, we were so that is about why SVG sucks so bad, and similarly for many other technologies, DOM and XML. So anyway, so let me read the comments a little bit. Uh, so it's like Forbidden 303. Forbidden, where are you from? What country or city? More important is the concept of coordinate systems. Okay, I think maybe we expand that because that's important. So have you ever played with Blender 3D? I tried 10 years ago, exactly 10 years ago, like 2008, 2009, when I was in Second Life. And I didn't go anywhere. So I tried it, for 2, 3 days. I didn't go anywhere. It has a Python interface. You mean Blender 3D? Okay, Blender 3D. It has a reputation of being extremely hard to learn. On the other hand, there are many other CAD systems, open source or CAD systems that has much more intuitive, more intuitive than Blender 3D. So Bartholomew says my internet was down for the past 20 minutes. Oh my god, I don't know why, but at least I'm back online. Oh, okay, okay. So you missed a big rant on SVG. Okay, I don't know if you caught that. So Forbidden says the convolution of programming languages drove me to Lisps. Okay, Scotland. Oh, Scotland. Ah, very interesting. Cool. It's much better now. Okay, so how long I've been talking? I'm thinking maybe that's like it. Oh my God, 1 hour and 16 minutes. Yeah, so let me go over. There's not much to this package. The devil is in the details. That's the thing. When you start to write, I mean, on the surface, creating SVG is just like just like this. That's the outline, that's the bottom. But the details is so many details, and when you write a plotting software, there's a whole ton of issues you need to solve, uh, like adaptive sampling and also the automatic range. You know that's lots of problem to sell to solve. Then you have to deal with asymptotes. Like for example, in this, I wrote down some of the problems I encounter and solutions. Some I have solutions already, some I do not. Some of these, it take days. Took me days to actually find a solution. For example, um, one is scalable canvas size problem. I mean, this is a big problem. Okay, now I know the solution. The problem is, you see, when you okay, let me show you actually the canvas size problem. Okay, you guys see it? Uh, oh, you guys cannot see it. Shit, part of it is hidden. Okay, so anyway, so when you plot, wild functions, you have situation like this. It becomes a thin strip, or you have situation like this. It becomes a vertical strip, depending on the function. On the other hand, you see, on one hand, you want it to be automatic range. So you got these problems, and how you solve it, it's hard. Okay, and this is why in the early days on Linux, many DVD players, they cannot, fucking find the aspect ratio. Like when you watch DVD on Linux, in the early days, they squash the picture, so that's funny. And I realized, so that is actually a problem because this is not, it's somewhat complicated to actually solve this problem. It's somewhat complicated. So I spent days to actually solve this, find out exactly what's going on. Like you do analysis on what exactly is the problem. What is it you want to do, and find out what exactly this is a problem, why it happens, and so on. And what is a desired result when this happens, or desired result when that happens. Then you have to find out how to implement those solutions. I mean, is this a coordinate problem in SVG, or is it a width and height problem, aspect ratio? And how do you do aspect ratio in SVG? SVG has aspect ratios, like, and also, it's fairly complex because also in a browser, it's not just SVG, because the SVG has to go into a browser. When you don't specify width and height, it actually automatically create a area. So lots of complexities are involved. Then you also go read the SVG standard. Oftentimes it's not clear. Like you think you are reading the standard, the spec, SVG spec, but it's not clear. And yeah, it's not clear because it is not really good, badly written, because nobody cares about it. So anyway, that's one of the problem, the aspect ratio and width height problem. The other problem is auto plot range problem. This we talked about already, because you do want a automatic range finder, but it's not easy. Anyway, we talked about that. And adaptive sampling problem we talked about, and we have a solution that's pretty good. That is, you plot it so the curve do not have kinks, do not bend sharply. Then you have asymptote problem. You see, this is a problem. Okay, look at this plot. You see that plot? That is a hyperbola. You see a dot over here. You see it kind of like goes like that and goes like, it's pretty ugly. Let me show you a hyperbola. Okay, sorry. So these are school book curves. You learn these curves in pre-calculus. Hyperbola is this, this kind of is kind of two of them, like shaped curves. So let me show you some. That's some of the ways to generate hyperbola. Okay, and here's more hyperbola. Hyperbola is a family of curves. That means there are many of them, but they are well defined. Anyway, let's not go into it. But anyway, all these, the white curves here are hyperbola. They have hyperbola like any conic sections, like ellipse and parabola. They have special optic properties. For example, if you shoot a ray, I forgot what's his. Oh yeah, okay. So if you have a hyperbola here, suppose they are mirrors. Suppose they are like mirrors, one-way mirrors or something like that. So if you have two light points here, you shoot a ray, laser. Think of it as a laser. You shoot a laser ray, and it will refract. It will refract, and in fact, if your light source is at this precise point, then doesn't matter which direction you shoot the ray, all the rays will refract into this exact point. Okay, and vice versa. So you can shoot rays from here or here, but so every parabola has two point called focus associated with it. That's the beauty of math. You have all these special properties. Anyway, so that's hyperbola, and these 2 points are called its focus, and focus. And so we've seen one property, that is optical property. Then there are other, lots of other properties. For example, this is a pedal property. So if you, okay, there's a lot to explain. So if you have a hyperbola, let me explain this one. If you have a hyperbola, okay, then you draw a circle that is in the middle of the, centered on the center of the hyperbola. Then this thing happens. Okay, so once you have a middle, then you draw a line from one of the focus to any point on the circle, any point on the circle. Then you draw a line perpendicular to it. So you see, we draw a line to any point of the circle, and then we immediately draw a line perpendicular to that. Now, this perpendicular line is a tangent to the parabola at some point. You see what I mean? So it's tangent. So you see, so you can also shoot a right here. Anyway, this property is called pedal. Okay. Anyway, so there are so many interesting properties. Okay. Now, why am I mentioning hyperbola? Because when you plot hyperbola, remember we are trying to plot it, right? We are trying to, for example, we are trying to plot a hyperbola, and I failed. I wrote my program. It works on sine. It works on equal angular triangle. So let's do hyperbola. It failed. Why? Because when you use a specific parametric formula, for example, if you use this formula to plot parameter, there are many formulas, by the way. But anyway, if you use one formula, what will happen is that the point will, we start at t equals to 0. Okay, so 0, then 1, 2, 3, 4, and so on. So the point will start here. Then the point will go there, here. You'll go up the hyperbola, and then the point will go into infinity. Okay, it will it will shoot to infinity. Then it will come back from the opposite direction of infinity. It will come back here. So it will come back here, then up to infinity again. Then come back from the other direction. Okay, so when you plot it, you got a problems. I'm not showing it here, but basically this is called asymptote. Asymptote. Okay, so that's another problem you have to deal with when you write a curve plotting function. Asymptote is basically a line that happens. For example, if you have, this is actually a hyperbola, and you have this axis, that's actually the asymptote. This graph, the red lines, are the equations of 1 over x, and 1 over x is actually a hyperbola. Okay, it's just kind of rotated. But anyway, when you try to plot 1 over x, you have another problem, which is the divide by 0 problem. So I need to fix that in my. Let's show you some actual example. Let's do that. Let's do some plotting, and that's it for today. What is this? Unit vector. Save. Okay, let's go back to. Okay, let's just plot it. let's create a another one. So okay, so for plot 4, and let's open it. Let's create a new plot at the top here, and this will insert it to plot 4. And let's just plot 1 over x. Okay, 1 divided by x. Let's say from 0.1, let's say 0.01 to 7. Okay, now go to browser, refresh. There we have it, a problem. This is another problem. It's a long page, you see. Oh my god, this is god. You see, so when you do this, lots of this happens. Okay, so let's not, so let's try 0.1. Okay, go back to browser, refresh. Okay, now that's better. Back to Emacs, 0.2, let's say okay, 7, browser, refresh. Okay, so you see, we got the x over 1 over x. Let's do some let's do some fun thing for today. Let's just say math.sign. Okay, let's do random. Let's see what we can do. X equals to cosine 0 to 7. Okay, sine cosine. This is gonna be a circle, I'm pretty sure. There it is, sine cosine. You see the labels, the axis labels is another very difficult thing to do, because on one hand you see you don't want them to overlap, but however, when the scale is very small, let's say from 0 to 0.1, you want to plot something that from 0 to 0.1. So in between all the numbers is 0 point something something, like a fractal, you know so you don't have, then you cannot, when you write the numbers they overlap. So how do you solve that? There's no simple answer. It's quite it involves AI. It involves elementary AI. That is, you need to figure out some smart way, some heuristics, so that your labels don't overlap. Maybe you slant the labels, and the most difficult part is that you want to make all this automatic. You don't want users to, oh, now, I see overlap, then I try to adjust, so they don't overlap. That doesn't work, because then you're gonna adjust it 10, 20 times. It's very time wasting. So if you want a good software, you need to have these automatic, so they don't do things like that. You want a automatic labeling system, so the label generated, they don't overlap, and also they just make sense for you, without you self, have to specify, where you want the label. Of course, that's optional. You can do that. You want to let users to specify at which point they want what labels. That would be good. But meanwhile, you want automatic labeling system. And the key things is that you want it to be, you know, you want it to be smart. Make sense. The labels make sense. So let's try sine x times. Let's try something like that. Okay, let's try divided by 2. Okay, let's see what happens. Oh, let's nest it. Let's nest sine. Okay, first of all, constant sine, math sine. Okay. Okay. so what is pi? So let's see. Okay. Okay, so we got the function here, and let's say sine x. Oops, something wrong. Let's say sine x. Maybe let's see what's this error. So what? Any comments? Am I still going? Okay, we're gonna shut down. We're gonna shut down in 2 minutes, something like that. So last words. Put your last words, and we're gonna shut down in 2 minutes. So let's see what's the error. Console uncaught syntax error. Identifier sign has already been declared. Oh, of course, yeah. So identify sign has already been declared. Oh, okay, right, yeah. So we don't need replot. There it is. What is this? Okay, let's go back to one way we can do is shrink it. Shrink doesn't work. So another way to solve this is actually create a we need to actually specify a user coordinate. I mean we need to specify a width and height. But let's not do it now. So let's sign let's see what happens. Why is it not going? Oh yeah, so if you have sign inside, that doesn't work because everything is just going to be 1. Okay. Oh, now, okay, so we got figure 8. Now let's see. Yeah, that's not good. Okay, we get some kind of Lijia something called Lijia. So let's put square root into the equation. Plus times math dot square root. Okay, x. Square root is spelled wrong, I think. Okay, anyway, that should be it. Okay, thank you guys for watching. That's it for today. Yeah, that's it for today. Any last questions? Post it, and bye Bartholomew, bye Forbidden. And whoever is here, bye. Have you done any Fourier series? No, actually, I have not studied Fourier series. Fourier series. It's one of the things that it's people talk about that often, but I actually never studied Fourier series much. Okay, bye guys.